a jeweler weighing a diamond. She weighs it once, 10.003 grams. Again, 9.998 grams. Same diamond, same scale, same room. So what's going on here? The diamond label or its specification sheet says it should be 10 grams. That's the nominal weight. But is it really 10 grams? How can we know? What is the true math of the diamond when every time we measure it on a high precision scale, we get a different reading? Welcome to the world of precise measurements, where every measurement reading comes with an error. In an ideal world, if the same thing measured several times, we get same result each time. However, in practice, in real world, it is not like this. Each measurement result is thrown off by a random chance error, and the error changes from measurement to measurement. That gap between the measured value and the reality is what this episode is about. Hi, welcome back to Lankers. Before we get into it, we need to answer a more fundamental question. Do these measurement errors actually matter? You see, the point is, if we don't understand error, we can't trust our data, and statistics allows us to move from a hunch to near certainty by estimating how much we might be off. More specifically, and in practice, in mechanical and structural engineering, if a measurement system is less precise than you assumed, components that appear to meet tolerance may be out of a specification. In manufacturing, if the gauge you use to inspect a part is not precise enough for the tolerance you are trying to hold, you will pass defective parts and reject good ones. So the measurement error has physical, financial, and human consequences. Therefore, knowing about measurement quality is important. But here is a foundational truth of this entire subject. All measurements are wrong. Not some measurements, not measurements made with cheap equipment, all of them, always, without exception. When you measure something, you record a value, but the true value of whatever you are measuring is almost certainly an irrational number, one that goes on forever and cannot be perfectly represented by any string of digits, no matter how many decimal places your instrument displays. This occurs because we model physical traits like weight or length as continuous variables that can take an infinite range of values, whereas our instruments are limited to discrete units. Every measurement is therefore off by some amount. It might be tiny, micrograms, nanometers, parts per billion, but it is never zero. So if measurement is both vital and always imperfect, how do we even function? Well, yes, all measurements are wrong, but the errors are not arbitrary chaos. They are random, and randomness, it turns out, is actually very well behaved mathematically. Consider a weather forecast. The Weather Channel predicts a high of 18 degrees Celsius. The actual high comes in at 20 degrees Celsius. So did they lie? Of course not. They just reported the most likely outcome, knowing that reality would land somewhere in a range around that prediction. Every model is wrong, every prediction is inaccurate, every measurement is imprecise. But the key insight is this: if errors are random, they follow statistical patterns. They cluster predictably. Their average behavior can be described. And if you can describe the error, you can work with it intelligently rather than being blindsided by it. And that's exactly where statistics enters, not as an abstract theory, but as the practical tool built specifically to handle this situation. That said, the matter of fact is, from school through university, we are trained on exact quantities. For example, F equals M times A equals MC squared. These are clean, deterministic relationships. By the time probability and statistics appear in a curriculum, they can feel like they belong to a different and fuzzier world. But statistics is not a workaround for sloppy thinking. It is the only rigorous language available for dealing with an inherently complex physical world. Every model is wrong, but a confidence interval identifies a set of models containing the truth with known probability. Every prediction carries uncertainty, but tolerance analysis lets you quantify and control how much of that uncertainty you can afford. Every measurement is imprecise, but a Gage R&R study tells you whether your measurement system is actually good enough for the job or not. So as engineers or scientists, we should make ourselves comfortable with these tools in statistics and statistical thinking. Now that we understand all measurements are random and imprecise and why statistics is the right tool to deal with it, let us build the conceptual framework that makes it all work. It starts with a single equation. Okay, this is the master equation behind any measurement, the one that everything else in this episode rests on. Every recorded measurement equals the true value, that means the truth that we are looking for, plus the chance error, plus bias. 3 components, 3 completely different natures. The true value is what the universe actually assigned to whatever you are measuring. It exists, but you cannot know it precisely. This is because the universe specifies physical quantities with infinite precision. Because a continuous scale like height or weight has an infinite number of possible points, the probability of the true value being a clean, terminating number is mathematically 0. Essentially, every measurement you record is just a rounded approximation of a value that actually contains an infinite string of digits, the true value. Then you get a chance error in every measurement, which is the random component. It fluctuates unpredictably from one measurement to the next. And the other component is bias, which is a systematic error. It pushes every single reading in the same direction every time you measure. So here is the most important practical implication of this equation. Because these components behave differently, they also require different solutions. You cannot fix bias by taking more measurements. You cannot fix chance error through calibration alone. So understanding which type of error you are dealing with is the first step to dealing with it correctly. So let us start with the chance error, the random component, because it is the most universal and the one that trips up the most people. The chance error is different every single time you measure, even when you control everything you possibly can. Same room, same instrument, same trained operator, same procedure, and yet each measurement comes out slightly different. Why? Because there are millions of microscopic physical factors acting simultaneously. Tiny fluctuations in air pressure, barely detectable vibrations in the bench. Nobody can track all of these factors individually. What we do know is how they behave statistically. The chance error throws each individual measurement off the true value by an amount which changes from measurement to measurement. The variability in repeated measurements actually reflects the variability in the chance errors. Now, given that chance errors exist in every measurement, there are 3 questions that naturally follow, and they frame the rest of this episode. Where exactly do these chance errors come from? The honest and somewhat uncomfortable answer is, in most real-world situations, nobody knows precisely. They emerge from the combined effect of countless tiny physical factors that no one can isolate and track individually. We accept that they exist without being able to fully explain them. Second, how big are these chance errors likely to be? This one we absolutely can answer, and it is the central practical skill in this episode. Third question, when you take the average of many measurements, is it possible that the chance errors cancel each other out? Also, since each measurement is thrown off by chance error, the average cannot be exactly right either. So, what is the likely size of the chance error in the average itself? That is one of the most important questions in all of applied statistics, and we will delve to it properly in a future episode. But for today, let's get back to question 2. There is a 10-gram check weight owned by the National Bureau of Standards, now called NIST, National Institute of Standards and Technology. Since 1940, this weight has been measured roughly once a week. Every factor known to affect results, air pressure, temperature, kept as constant as humanly possible. And it is called a check weight because its job is to monitor the measurement process. If the readings on NB10 suddenly shift, something in the system has changed or broken. It serves two purposes simultaneously: quality control for the measurement process and a long-running record of what chance error actually looks like in practice over time. So what we mean by quality control? If the measurements on NB10 jump from 400 micrograms below 10 grams to 500 micrograms above 10 grams, something has gone wrong and needs to be fixed. For this reason, NB10 is called a check weight. It is used to check the weighing process. Here is a second reason why repeated measurements matter, and this one is very practical. Imagine a scientific laboratory has a weight and they need that to be calibrated. They package it, they send it to the National Standards Office, then a technician weighs it carefully, following every procedure, and sends back a result. Now the laboratory has a number, but should they trust it completely? They probably should not, at least not without knowing how much chance error might be hiding in that single measurement. So how do they find out? One straightforward approach is to send the same weight back and ask for a second weighing. Okay? Then compare the two results. If they come back within a few micrograms of each other, that tells you something important. The chance error in each individual weighing is probably only a few micrograms in size. But if the two results differ by several hundred micrograms, then you know each measurement could be off by several hundred micrograms, and a single reading is not nearly as reliable as it looked. That is a perfectly valid approach. The problem is, it is slow, expensive, and inconvenient for everyone involved. This is exactly where NB10 repeated measurements matters. Because the Bureau of Standards has been weighing NB10 week after week for decades, all of that information about how much measurements vary from one weighing to the next is already sitting in their records, right? Any laboratory sending in a weigh for calibration does not need to ask for it to be weighed twice. The Bureau already knows how repeatable its own measurement process is. The work has been done in advance once, and it answers the questions for every calibration that follows. So this brings us to the most fundamental point in all of measurement science. No matter how carefully a measurement is made, it could have come out slightly differently. If you went back and repeated it right now, it would come out slightly differently. The question is always by how much? And the only honest way to answer that question is to actually replicate the measurement and look at the spread. Everything else is just guesswork. We are going to look at 100 of these measurements, and they are going to teach us something precise and permanent about the nature of measurement error. So here is what those 100 measurements actually produced. So all 100 measurements cluster around 400 micrograms below 10 grams, which tells us NB10 is actually slightly lighter than its nominal value, which is 10 grams. But the individual readings are not all the same. The smallest came in at minus 375 micrograms and the largest at minus 437 micrograms below 10. That is a spread of about 60 micrograms across 100 measurements of the exact same object by the same team on the same machine with the same procedure. To put the scale in perspective, 400 micrograms weighs about as much as a grain of salt. This is extraordinary precise work, and yet every single reading is still uniquely wrong by some small amount. So not one of them captured the exact true weight of NB10. This is chance error, visible in real data, which raises the central question now. If none of these measurements are exactly right and the true value is unknowable, what can we actually conclude from this data? So, here is the single most important concept in this episode. Write this down. The standard deviation of a series of repeated measurements estimates the likely size of the chance error in a single measurement. In other words, the variability in repeated measurements reflects the variability in the chance errors, and both are gauged by the standard deviation of the data. Mathematically, the standard deviation of the chance errors must equal the standard deviation of the measurements. We showed this by the carryover rule, which we discussed in our previous episode, where we had a deep introduction into what is standard deviation and how it behaves. We learned that adding a value to a list of numbers is just a change of scale and does not change the standard deviation. Remember, in a stable measurement system, these random variations we call chance error are just as likely to push a reading high as low, and crucially, their average over many measurements tends towards zero. This is a very important property. So for NB10, the standard deviation across 100 measurements was just over 6 micrograms. That means any individual measurement of NB10 was typically off from the true value by approximately 6 micrograms. Errors of 2, 5, or 10 micrograms happened fairly regularly. Errors of 50 or 100 micrograms essentially never happened. And here is the practical power of this. If another laboratory sends a 10-gram weight to the Bureau for calibration, they do not need to send it twice to estimate their uncertainty. Bureau's decades of NB10 data already tell them the chance error in this measurement process is approximately 6 micrograms. The work has already been done. Now, let us make this concrete with actual numbers from the dataset. Let us put some real numbers to this. The average of all 100 NB10 measurements was 405 micrograms below 10 grams, and that average is our best estimate of the true weight. Not perfect, but the best we can have. Okay. Now take the very first measurement in the table, which come in at 409 micrograms below 10 grams. So how far is that from the average? 409 minus 405 equals 4 micrograms. So that 4 micrograms is the chance error in that single measurement. Now, measurement 2 came in at 400, which is 5 below the average. So a chance error of -5. Across all 100 measurements, the typical size of these deviations was about 6 micrograms. That is the standard deviation, which tells the size of random chance error here. It comes directly from the observed spread in the repeated measurements. It is empirical and it is a direct measure of deviations from the average. If you are not fully familiar with standard deviation, we have covered this in our episode on the average and standard deviation. Please check that out. But besides that, the NB10 dataset forces an important question. If you look closely, 3 of the 100 measurements fell so far from the average that under a normal distribution, they should be essentially impossible. So measurement number 36 is 3 standard deviations away from the average, and measurements 86 and 94 landed approximately 5 standard deviations from the mean. The probability of that under a perfect normal curve is vanishingly small. Look at the histogram distribution of measurements. These are called outliers. The Bureau of Standards investigated thoroughly and found no explanation, no equipment malfunction, no procedural error, no blunder of any kind. They simply happened, and their effect on the data was measurable. Those 3 strange readings actually inflated the overall standard deviation from 4 micrograms, the value that describes the other 97 well-behaved measurements, up to 6 micrograms for the full dataset. So the normal curve fits the 97 data points reasonably well, but it does not fit the full 100 data points. And this is because of the outliers. So this type of tension is something that statisticians must confront honestly. So what should you do when you encounter an outlier? This is one of the most ethically loaded questions in data science. So the Bureau of Standards addressed the outlier question directly and with unusual bluntness. When analysts collect measurement data and something unexpected shows up, a reading that is too high or too low or just awkward, there is a very human temptation to make it disappear. Sometimes this is conscious, sometimes the analyst does not even realize they are doing it. They set a performance limit, they call the reading as abnormal, and then they remove it. The data looks cleaner, the results look better, everyone is more comfortable. But the Bureau was blunt about what this actually does. Throwing out data based on arbitrary limits does not improve your analysis. It can destroy it. You are no longer measuring how your process actually behaves. You are measuring how you wish it would behave. The rule is simple. You can only reject a measurement if you can point to a specific documented reason why that particular measurement went wrong. A power surge, for example, a door slamming at the wrong moment, a known measurement malfunction. If you have a real reason, fine, reject it and write it down. If you do not have a reason and the number simply looks inconvenient, you should keep it. Now here is the uncomfortable part. When an outlier appears, you face a genuine choice. Either you ignore it or you confess that your measurements do not follow the normal curve. And because the normal curve carries so much theoretical prestige, so much elegance, so much authority, the first option is almost always the one that wins. The outliers disappears quietly and the normal curve survives. Now we have covered chance error, but there is a second type of error that behaves completely differently, and it is in many ways more dangerous. Bias. Bias is the systematic error in the master equation. It is completely invisible if you only look at your own data. Imagine a butcher who weighs your steak with his thumb quietly pressing down on the scale. That is not random. Every single reading is elevated by roughly the same amount. That is bias. The critical difference from chance error is that chance errors are equally likely to be positive or negative, so they tend to cancel out when you average many measurements. Bias, on the other hand, does not cancel. It bends every reading in the same direction, so you could take 1 million measurements and their average would still be wrong by the full amount of the bias. And here is what makes it so sneaky. You typically cannot detect it just by examining your own measurements. You need something external to compare against. So let's look at a real national scale example of bias that shows why more measurements never fix it. Here is a bias at a national scale. The US national prototype kilogram, called K20, was compared to Legrand K, the international prototype for the standard kilogram held in Paris. The comparison found that K20 was approximately 19 parts per billion lighter. That is tiny, but it was systematic. So every weight measurement made in the United States was off by the same fraction every time. The Bureau corrected for it by revising all calculations upward by 19 parts per billion. That correction required an external standard. There was no way to detect or correct the bias from within the US measurement system alone. Here is an analogy to better clarify this. You cannot determine the exact height of the Emperor of China by averaging the guesses of 1 million citizens who have never seen him. Okay? If every guess is anchored to the same incorrect legend, averaging produces a very precise version of the same wrong number. More data does not fix a bias process. Only calibration against an external reference does. So this distinction between fixing chance error and fixing bias brings us to the full picture of what measurement quality actually means. Here is one of the most important distinctions in all of measurement science, and it is one of the most commonly confused in practice. Precision and accuracy are not the same thing. Precision is about how close your measurements are to each other. If you fire 10 arrows and they all land in a tight cluster, you are precise, your chance error is low. Accuracy is about how close your average is to the truth. If those 10 arrows cluster tightly in the upper right corner of the target, tight together but away from the bullseye, you are precise but not accurate. You have a bias problem, not a chance error problem. The solutions are completely different. Precision problems require you to reduce random variation through better instruments, more controlled conditions, more replication. Accuracy problems, however, require calibration against an external standard. The goal is always to achieve both. Now we understand what can go wrong with measurement. Let us talk about what we actually do about it in practice, starting with the most fundamental intervention. So how do we actually deal with measurement uncertainty in practice? The first and most fundamental intervention is calibration. When you buy a pack of cheese labeled 500 grams at your local supermarket, the scale at your local supermarket isn't just trusted on faith. It is checked periodically by local weights and measure inspectors, for example, in the UK, that is the trading standards, and then these officials carry their own highly accurate standard test weights to verify the scale. But how do we know those standard weights are right? Those too must be calibrated. They are actually sent off to be calibrated by some national standards. In the UK, they go to the NPL, the National Physical Laboratory. But every country in Europe has one of these temples of precision. Still, these national institutes should also calibrate and compare their standard reference weights with some other source of truth, right? But where is the end of this chain? A small cylinder of platinum and iridium known as Legrand K, which is the nickname for the international prototype of the kilogram. By an international agreement known as the Treaty of the Meter, signed in 1875, 1 kilogram was defined to be the weight of this object under standard conditions. Each country that signed the Treaty of the Meter got a national prototype of the kilogram whose exact weight had been determined as accurately as possible relative to Legrand K. Then all other national standard weights got determined relative to this national prototype. So there is a chain of comparisons here. Your supermarket, your local inspectors, your national laboratories, and then international prototype of the kilogram. So this means that if Legrand K got a fingerprint on it or changed mass over time for whatever reason, the entire world's measurements technically would have become heavier or lighter. Now, one important update to add here. In 2019, the international scientific community made a historic decision. They voted to redefine the kilogram, not in terms of a physical object, but in terms of a fundamental constant of nature called Planck's constant. No more single cylinder ruling all mass measurements. The new definition is based on the universe's own mathematics, which doesn't wear down, doesn't get contaminated, and can't be stolen. But the old story, the century-plus reign of Lagrange K, is still the framework that explains why measurement calibration is a chain and why we need standards. So, getting back to measurement errors, the accuracy in weighing at a supermarket ultimately depends on accuracy of calibration work done at the national office responsible for maintaining standards, okay? This full documented chain of comparisons is called traceability, and it is a mandatory requirement in quality systems like ISO 9001. Calibration is the mechanism that catches and corrects bias. It is how you ensure your average readings are close to the true value, to the truth. But here is the important limitation. Calibration addresses accuracy, not precision. Okay, it does nothing about the random variation, the chance error. That still exists in every individual reading after calibration. So for that, you need a separate tool. And that tool is the Gage R&R study, which takes the statistical thinking we have built throughout this episode and applies it directly to evaluating whether your measurement system is good enough for the job or not. Here is how it works briefly, only as an introduction. In a Gage R&R study, you take several samples of the same thing. You have multiple operators measure each sample multiple times in randomized order without knowing what the other operators recorded. You then analyze the spread in those measurements statistically, separating the variation that comes from real difference between parts from the variation that comes from the measurement system itself. So the output tells you what fraction of your total measured variation is actually measurement error. If that fraction is small relative to your tolerance, the gauge is acceptable. If it's large, if the measurement system itself is a significant source of variation, then the instrument is not suitable for the job, no matter how recently it was calibrated. So calibration and Gage R&R work together. One is not a substitute for the other. So we have now covered everything, what is happening, how to quantify it, and how to work around it. So let us bring it all together. No measurement is ever perfect. Every recorded value carries chance error, bias, or both, no matter how carefully it was made. Before you rely on a measurement, you should estimate the likely size of the chance error. The best way to do that is replicate the measurement. The standard deviation of a sequence of repeated measurements made under the same conditions gives likely size of the chance error in a single measurement. Bias or systematic error causes measurements to be systematically too high or systematically too low. The equation is individual measurements equal exact value plus bias plus chance error. The chance error changes from measurement to measurement, but the bias stays the same. Bias cannot be estimated just by repeating the measurements. Even in careful measurement work, a small percentage of outliers can be expected. The average and standard deviation can be strongly influenced by outliers. Then the histogram will not follow the normal curve. Precision and accuracy are not the same thing. Precise means tight, accurate means centered on the truth, and you need both. Thanks for watching. Until next time.